Welcome back. Let's finish up the rest of the problems from section 3B's assessment preparation. Last time we left off on problem number 42 is the last one we finished. We're ready to start on problem number 43. So 43, the instructions just say answer the question. Find the scale ratio for a map if 1 centimeter represents 100 kilometers on the ground. 1 centimeter on the map represents 100 kilometers on the ground. So I'm using this colon to represent a proportion. And so I'm going to write this as 1 times 10 to the negative second meters. And I'm going to say this is 1 times 10 to the second times 10 to the third meters, because kilometers are kilo, which is 10 to the third. And so I want to get a 1 on this left-hand side. So I'm going to multiply both sides by 10 to the second. And the meters are going to cancel out here. So 1 is to 1 times 10 to the second times 10 to the third times another 10 to the second. It's 1 to 10 to the seventh, right? Or 1 to 2, 3, 4, 5, 6, 7. 1 to 10 million. Right, that's my scale, 1 to 10 million. So that was problem number 43. 44 is quite a bit harder because it's in the engineering system, or USCS, US customary system. 1 inch on the map represents 10 miles on the ground. And so we need to have a conversion factor here that converts inches to miles or miles to inches. So 1 mile is 5,200 feet, or 5,280 feet. And so let's make this miles. So this is times so miles are on the bottom, 1 mile, and this is 5,280 feet times 1 foot is 12 inches. Feet will cancel, miles will cancel, the inches will cancel out here. This is going to be 1 to 10 times 5,280 times 12. Let's figure out what that is. 10 times 5,280 times 12 is, oh, let me get this off the scientific notation. Back in mode here. 1 to 633,600. Okay, so now let's find the scale ratio if 3 centimeters on the map represents 0.6 of a kilometer on the ground. So again, let's change everything to meters. right? And I want a 1 on the left-hand side. So this is going to be 0.2 times 10 to the 5th. So when I change that to standard form, what are they calling it? Maybe not standard form, but ordinary form. 1, 2, 3, 4, 5 zeros in front of it, and the 2. Okay, that is my oh, I went the wrong way. I knew that didn't look right. That's why this is quantitative reasoning. Make sure that your answer makes sense. So this is a positive 5. I should have 1 to 20,000 centimeters are smaller than kilometers. So one of these should, anyways, yeah, there's a much bigger number on this side than there is on this side for the scaling factor. So I was scaling up. My map was needed to be made bigger to represent real life, not smaller. All right. That was number 45. Let's look at number 46 here. 6 inches represents 7 miles in real life. So we already have this that we did before. We have 7 miles times 5280 feet per mile times 12 inches per foot. We're going to need to multiply both sides by 1/6 as well. Get this to be 1. And then we have 6 goes into 12 2 times. This is 7 times 5280 times 2. Seven times 5280 times 2 should be 1273920. So for 47, find the scale ratio for a map if 4 centimeters represents 10 kilometers on the ground. You're going to see that it's much easier if this is in metric, and we can deal with the units just canceling like that. I'm going to automatically take these over here. So 1, 2, and then this is going to be 2.5 times 10 to the 5th. It's 1 to 2, 5. Zero, 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 zero. Okay. And that's 47. 48. Suppose you are constructing a scale model of the solar system using a scale ratio of 1 to 10 billion. Million, thousand units, 1 to 10 billion. In your scale model, what will the diameter of Jupiter be in meters? The diameter of Jupiter is 143,000 kilometers times. So this is going to be 1 meter is going to represent 10 billion meters. And this is, so let's use scientific notation here. 1.43 times 10 to the 2, and 3 is 5, plus another 3 is 8, times 1 times 10 to the 1, 3 is 4, 7, that's 10. These are meters, these are meters. Those are going to cancel out. So this is going to be 1.43 times 10 to the negative second meters. Or we could call that 0.0143 meters. Another way to talk about that is we can call that, these are decimeters, centimeters, millimeters. So, and we really don't talk about, after that, we could say that this would be 14.3 millimeters. This is the answer the teacher wanted, I believe. Let me make sure, number 48. Wanted to go to meters. She specifically said she wanted the answer in meters in the problem. Just to know, when we got small numbers like that, we usually refer to them in a smaller unit that would make sense to people, because 0.0143 meters usually doesn't make as much sense to people as us saying 14 3/10 of a millimeter. I'm like, oh yeah, I kind of get that. I can wrap my head around just how big that is. Okay, so let's clear this. Let's move on to number 49. Suppose you are constructing a scale model solar system using a scale ratio of 1 to 100 billion again. Your scale model, what will be the distance from Neptune to the sun in meters? The distance from Neptune to the sun is 4,497 kilometers. So we're going to have to use the scaling ratio of 100 billion meters will be represented by 1 meter. And so this is going to be 4.497 times 10 to the third meters. And that's going to be represented by 1 meter. And this is going to be 1 times 10, this is already to the second, times 10 to the, now billions, so that's going to be 10 to the, got units, got thousands, we've got millions, right? So this is going to be 1 times 10 to the 9th to get a billion, right? So this is going to be 4.497 times 10 to the 3 minus 11 meters is going to be oh, this is not 3. This is 3 times 10 to another 10 to the 3rd for the kilo. So this is going to be 6 minus 11. This is going to be 4.497 times 10 to the negative 5th. Let's look at this again. 3 and 3 is 6. And that is 11. It's negative 5. So meters. And well, let's just do it this way instead then. Since I have it in kilometers to start off with, let's go kilometers and then let's change kilometers to meters. That's easier. So let's say that 1 kilometer in our scale model will represent 100 billion kilometers. And if this was, oh, I forgot the word million. Ha, that's what's wrong. That's a big difference. I was like, that's not enough kilometers to go all the way to Neptune. Million kilometers. Okay. So this is 4.497 times 10 to the 9th times 1 over 1 times 10 to the 2, 5, 8, 11 kilometers. So this is 4.497 times 10 to the negative 2nd kilometers. But kilometers, you want to go to meters. This is going to be 44.97 meters. Okay, sorry. Let's go ahead and do number 50. Suppose you're constructing a scale model of a solar system using a scale ratio of 1 to 200 billion. Your scale model will be the distance from Saturn to the sun in meters, the distance from Saturn to the sun is 1,427 million kilometers. So we need 200 billion kilometers is going to become 1 kilometer. Million is going to be times 10 to the sixth. Billion is going to be times 10 to the ninth, right? Units, thousands, millions, billions are another set of 3 zeros. So this is going to be 1427 over 200 times 10 to the negative third kilometers. But kilometers are ten to the third meters, so those are going to go away. So let's just change this so that this is in thousands here. It's just going to make it easier for me if I multiply top and bottom by 5 to do this without a calculator. 13, 21, 7 over 1,000. So that's going to be 7.135, like that, meters. Yeah, that's the right answer. You can do this in the calculator though. 1427 divided by 200 and get your 7.135. One more in this section. Distance from the Earth to the Sun is about 1.5 times 10 to the 8th kilometers. I'm so glad this one got written in scientific notation. While the distance from the Earth to the Moon is about 3.8 times 10 to the 5th kilometers. This is the smaller distance here, right? The scale model of the solar system is constructed so that the distance from the Earth to the Sun is 100 meters. And 100 meters is the small part. So 100 meters is to 1.5 times 10 to the 8th kilometers as what is to 3.8 times 10 to the 5th kilometers. Okay, so this is a proportion. Let's go ahead and let's simplify this proportion a little bit here. The kilometers are going to make each other go away. In this, let's make this 1 to 1.5 times 10 to the 6th by multiplying both sides by 10 to the negative second. So let's write this as a proportion like this. Shouldn't use X because that looks like multiplication. Let's write a question mark for that. Right, like this, and 10 to the 5th divides out and leaves me with 10, and this is going to be 3.5 over 15 is equal to question mark. 5 goes into here. Let's just do this on the calculator now. 3.5 divided by 15 is lost track of some decimals. Let's try this again. Sorry. So we're going to, how much bigger is the, how many of these, let's find the ratio of these two things. So we want to go Earth to Sun, Earth to Moon, let's say. So our two ratios that should be same are going to be in the in real life. Earth to Sun is 1.5 times 10 to the 8th kilometers. Earth to Moon is going to be 3.8 times 10 to the 5th kilometers. And that needs to be the same as Earth to Sun is going to be written as 100 meters, which is 1/10 of a kilometer. And this is my unknown here, and I'm going to find it in kilometers and then change it to meters. So kilometers will cancel out here. This is going to be 1.5 divided by 3.8. It's going to be 0.3947368421 times 10 to the 3rd. Multiply both sides by 10 and say that this is going to be 3.947368421 times 10 to the 5th. That's 1 kilometer, right? So this is going to be in and this is going to be times question mark. So I want to divide by this crazy number here. Question mark times that question mark times this. So let's take and make this question mark equals 1 over 3.947368421 times 10 to the 5th. And this is a kilometer, so this is 10 to the 3rd. We want the answer in meters. So 1, let's just use the reciprocal button. button. 2.53333. This is just threes repeating forever, times 10 to the -2 meters, right? I'm off by a power of 10. Oh. Yeah, I'm off by a power of 10 because this is 1/10 here of a kilometer. So this is 1/10 of a kilometer is going to only be times 10 to the second. That makes that -3rd. Then that makes that Did I get the right answer? Hope I'm not off by a power of 10. I am. The answer is supposed to be this. So let me try one more time. Sorry, you guys should see that this is the way that it is sometimes. 1.5 times 10 to the 8th. That's the big one. All right. So let's see how many little ones we have in the big one. So, or no, how many big ones we have in the little one. So that's what I did backwards. So let's do this. This is 3.8 times 10 to the 5th divided by 1.5 times 10 to the 8th. That is 3.8 times 10 to the 5th divided by 1.5 times 10 to the 8th is going to be that needs to be multiplied times my big one here is going to be 100 meters. There it is. So, and I'm going to get 0.253 meters, and she approximated that as that. Okay, ask me questions later if you need to, but that's how you can use your calculator to multiply or divide and get the answer. Let's move on to number 52. Given here, the annual energy consumption is roughly 1 times 10 to the 20th joules. Express this as energy consumption per person per second. Energy consumption per person per second. So first we need to find per person. So divide by the number of people. So this is 280 million. This is per year. So this is 1 times 10 to the 20th joules per year per 280 times 10 to the million is going to be sixth. People is going to be 1 divided by 280 is 0.0035714,286 times 10 to the 14th joules per person. And this is per year. Now they want to change this to per second. So we need to take that number. We need to say that 1 year is 52 weeks. 1 week is 7 days. 1 day is 24 hours. And each hour is 3,600 seconds. So this is going to be um, 0.035714286 divided by quantity 52 times 7 times 24 times 3,600. And that makes my years cancel out with my years, my weeks with my weeks, days with days, hours with hours. And this should be 1.13560382 times 10 to the negative 10th joules per person per second, and this was times 10 to the 14th times 10 to the 14th, sitting there. So this is 1.13560382 times 10 to the 4th joules per person per second. I'm going to move that decimal place 4 places to the right. 1, 2, 3, 4, 1, 1, 3, 5, 6. Three. I'm off by some rounding. Is all that it is. It's the same. It's the same answer. I think we're just off by mere decimal places here from rounding here. So 11324.9 is what she has. Is joules per person per second. So and that probably has to do right here with whatever rounded to be that 6 was significant. And I just cut it off with the 6. So try not to round and round and round again. Go ahead and stick it all in if you can. Like we said, let me just try that again here. If we have 1 times 10 to the 20th divided by, and in parentheses, we have 280 times 10 to the 6th times 52 times 7 times 24 times 3600 . Yeah, see, I get slightly different answers. Did I write something down wrong? Nope. So, I have to ask her about that one because I think this is a more exact answer. I don't think I got any of my conversion factors wrong here. There's 52 weeks a year, 7 days in a week, 24 hours in a day, 3,600 seconds in an hour. And so this should be according to the work that I have, this should be 11356.0. So go ahead and figure that out later. If you guys have questions about that, check my work, make sure I was right. I can make mistakes too. Population of the United States in 2000 was roughly 280 million people. Express this as the number of people per square mile if the area of the United States is roughly 3,536,000 square miles. So we want people per square mile, 280 million divided by 3,536,000. Since people per square mile is going to be 2.8 times 10 to the 258, 3.3536 times 10 to the 6th, 2.8 divided by 3.536 is go to 2 place values. 9 times 10 second is going to be 79 people per square mile. Okay. Speed of light is approximately this really big number. I'm not even going to try and read right now. Miles per year. Express it in miles per second. So 5.866 times 10 to the 3, 6, 9, 12 miles per year times 1 year, 365 days times, I wish I just had a conversion go from right from one to the other already, but 1 day, 24 hours times 1 hour is 3,600 seconds. So I'm going to make this 5.866 times 10 to the 12th. Miles per second over 365 times 24 times 3,600. 5.866 EE 12 divided by 365 times 24 times 3,600. Close parentheses for the denominator, close parentheses for the fraction. It's going to be 86,009.6 miles per second. Now compare that to, we were already given a number somewhere. .86 times 10 to the 5th miles per second was given to us in problem number 37. It says approximately. So this is a good answer because 1, 2, 3, 4, 5, that jives with what we were told in number 37. So we were already given our speed of light in miles per second earlier. So that's good. Let's do number 55. Worldwide, there are approximately 132 million births per year. Express this quantity in births per second. So again, we're making about the same conversion, but let's do 132 million births per year. A year is going to be 52 weeks. A week is 7 days. A day is 24 hours. And an hour is 3,600 seconds. So years cancel with years, weeks with weeks, days with days, hours with hours. We're going to be left with 132,000,000 divided by parentheses 52 times 7 times 24 times 3,600. And that's going to give me 4.197191697 births per second. And I'm going to go back to sig figs here. Had 3 sig figs, so I should make this 4.20 births per second. That 0 is significant because it is the third significant figure. It means that I took a place value that was to the right of this 9, and rounded that 9 up to a 10, that it was either 0.19 something bigger than 5, or it was 0.20 something smaller than 5 over here. So somewhere between 0.195 and 0.204 is what that tells me, that I rounded it like that. Rounding is going to actually come up in the next video in 3C. All right. And national debt was about $6.9 trillion in 2003. Express the quantity as the number of dollars per person, assuming that the US population at the time was 280 million people. So we've got 6.9 times 10 to the 9th dollars divided by 280 times 10 to the 6th people was going to be, it's 10 to the 3rd. So 6.9 divided by 280 is going to give me 0.02464285571 times 10 to the 3rd dollars per person. So let's make this dollars and cents because we're talking about money. So this is going to be 1, 2, 3. This is going to be $24 and trillion. Oh, hang on. This is 12. Million, billion, trillion. So that's 12. This is 10 to the 6th. So 1, 2, 3, 4, 5, 6. The decimal point's going to go there. It's 42.86 dollars per person. So trillion, T, 12. That's how I remember that. Trillion, 12. And millions is 9, millions is 6, thousands is 3. And we usually don't do the number of trillions, usually. So, but at that time, it was roughly $25,000 a person in debt. Back in 2003, it's way more now. So that's the end of this video. Again, took us about an hour. Sorry, I stumbled through some of the problems. Still am concerned that one of my answers doesn't match what's on the answer key. So we'll get that straightened out eventually. Go ahead and ask your instructor if you have a question about that. We have one more video left before the end of the material for what is unit or chapter 3. So so be ready for 3C coming up, which is on your estimations, your rounding, and things like that. Have a good day.